Hey everyone, I'm Shamal, and I'm going to be talking about distribution-free testing of decision lists with a sublinear number of queries. And this is joint work with Shi Chen and Yu Mao Fei. So we're going to start by talking about the testing versus learning problem. And in order to discuss that, we'll begin by defining pack learning. So in the pack learning model, um, we're given an unknown Boolean function f, which is promised to come from some known class of functions c, and as well as an unknown distribution d. And we want to learn a hypothesis H via labeled samples, where the samples are drawn from the distribution D, such that our hypothesis agrees with F for most values under the distribution. And we likely succeed because there's some randomness in the samples that we get from the distribution. Um, but now the motivating question is sort of in this pack learning setting, we're promised that the function comes from the class. But oftentimes, in practice, when we're running these learning algorithms, we don't actually know that the function belongs to the class. Um, and so, oftentimes what's done is sort of you gather enough data to learn, you try to learn. If you succeed, you're happy. If you fail, the function is not in the class and you're done. But kind of the question that we want to know the answer to is whether or not there's a more data efficient way of doing this. So this kind of motivates the distribution-free testing model. So here we're going to fix a class of Boolean function C. So think of this as like the class that we were trying to learn before. And a distribution-free tester is an algorithm that is given query access to an unknown function f, as well as samples to a distribution d. And so note that the queries are sort of a new feature here. We didn't have that in the learning model. But this ends up being kind of necessary for if you want to get non-trivial guarantees. And the tester should output except if the function is in the class, and it should reject if every function in the class has high error, right? So they all disagree with our function with, probability 0.1. And of course, these things are randomized, so you'd like them to succeed at sort of making this distinction with probability at least 2/3. So the first observation about this model is that testing is no harder than learning, and this was shown by Goldreich, Goldrosser, and Rahn in the paper that initially sort of put forth the model. So how do we conclude this? So to do this, we, essentially we'll use our learning algorithm. So we'll draw some samples from the distribution, and then we'll use our learning algorithm to learn a function g in the class. We'll assume that it uses a hypothesis in the class, such that it has low error. Then we'll just verify that actually the function that we learned is close to, the hidden function f by drawing a few more samples. And, if it is, then we'll accept because, we have a certificate that f is, at least close to something in the class. And if it's not, then we'll reject. So now, clearly, if it's not, we'll never accept or unless this step goes wrong. And, if it's in the class, then, we probably should have succeeded to learn it. And so this should be fine. The only caveat here is, I'm telling us of a proper learner to find something in the class. In general, the hypothesis in pack learning is not required to be in the class itself, but it turns out that information theoretically, it's fine to assume you have a proper learner. This distinction maybe matters a little bit more if you care about sort of the computational aspects of learning. But we're mainly going to be focused on query complexity in this talk. And so sort of the baseline we're going to be comparing to is sort of learning via this, like proper learning is yeah, great. So now, what are some example classes that people are interested in learning and testing? So one is k-juntas. So we say that a function is a k-junta if it only depends on k of its n inputs. So for instance, in this example here, we have x1, x4, x2, and this is a 2-junta because it only depends on the first two inputs of the function and doesn't depend on the rest. There's also conjunctions. We say that f is the conjunction if it's the and of literals. So here, in this example here, it's x1 and x2 and not x7. There's half spaces. F is a half space intuitively if sort of the points it labels as 0 and the points it labels as 1 can be separated by a hyperplane. Finally, there's decision lists. And these are a little bit notationally hairy to define. So I'll sort of maybe just describe what they are. There's essentially this like sequence of if-then statements. So at every stage you have a literal, And if it's satisfied, you sort of output the thing, and if not, you go to the next thing, right? So here, for instance, look at the first coordinate. If the first coordinate is a 1, we would output 0. If the first coordinate was not a 1, we would go to the next thing. And when you look at this literal, if it's satisfied, we output 0. Otherwise, if x3 is a 1, we go to this thing. If x2 is a 1, we'll output 1. Otherwise, we default in output to 0, right? So hopefully that gives like a reasonable intuitive understanding here. Great. So now what's known in this sort of testing versus learning model? So first off, it's known that, for conjunctions, we actually only need n to the 1/3 queries to test whether something is a conjunction. And now this is much better than learning, which requires, theta of n samples. For decision lists, we don't have any upper bounds, but we do know the lower bound for queries from this paper by Chen and Shi also applies here. And then, again, needs n samples to learn. For half spaces, it turns out that actually you can only improve on learning by, possibly logarithmic factors, because we kind of have logarithmic, you have an O tilde, omega tilde of n lower bounds are both sample-based, as well as if you have queries. Finally, for K-Huntas, we know that, if you're only allowed to get samples, then, you need exponentially many samples. And otherwise, actually only, O tilde of K suffice if you can make samples and queries. And learning requires, exponentially many points. So this is a big improvement for testing versus learning. Great. So our main result is going to be that, there's a tester for decision lists that is better than learning. And, decision lists were interesting because, they sort of lie in between this class of conjunctions and half spaces. Every conjunction is a decision list, every decision list is a half space. And, it's nice that the answer, so we expect the answer to be in between, but it wasn't clear sort of, where exactly it should have been. We also show a square root n lower bound, showing that which means that it's strictly harder to test than conjunctions. So it's sort of like in this strictly in between these two classes in some sense. And then finally, we show that, if you're only allowed to get samples and you can't make queries, then actually even for conjunctions, you can't beat learning by more than a logarithmic factor. And the same holds for decisions as well. Great. So in order to sort of talk about the ideas of sort of how we get the upper bound, we'll first talk about this new problem of testing total orderings. So here we're given a comparison function, which, what does it do? If we're given a pair and we evaluate on the comparison function, it's telling us which one is bigger, let's say, right? We're also given a distribution D, which, is unknown to us, but we have sample access to, over, various pairs. And we want to distinguish whether F is a total ordering or is far from every total ordering. So what I mean by far, I mean that, every total ordering disagrees with, our comparison function on at least 10% of pairs. And, as kind of a warm-up to our result, we show that, the distribution-free testing of total orderings requires roughly root n samples plus queries. So let's start with the lower bound. So to get the lower bound, we'll choose a random permutation and divide the numbers from 1 to n into groups of 5. We'll then sort of make these like 5-cycle type of things, and the distribution is going to be on these black edges here, right? And so now how should you read this? We have that pi of 1 is bigger than pi of 2, which is bigger than pi of 3, which is bigger than pi of 4, which is bigger than pi of 5, which is bigger than pi of 1, right? So right off the bat, we can observe that, this comparison function is 1/5 far from any total ordering, because, you sort of can't have a cycle like this in a total ordering. So every total ordering has to get at least one edge wrong here. And good. And on the other hand, how do I compare things between these? So sort of, I'll say that everything in this first group is less than everything in the second group, which is less than everything in the third group, and so on and so forth. So I have sort of, there's a total ordering between them. Great. And so now the thing to note is that, if you want to find a violation, so something that doesn't look like it's a total ordering, you need to find 2 cycles from two edges from a cycle, which will require square root n samples by a birthday paradox. And it turns out that actually queries won't help you find these any faster. So this will give us a square root n bound. So, like if we find two edges, we clearly can reject. So like, if we find pi 1, pi 5, pi 3, pi 4, we'd see this 4 cycle and we could reject. But, if we only get one edge, everything kind of looks consistent with being in total ordering. Now, technically, you don't need a violation to actually put this lower bound, but it turns out that this is easier to think about, and actually the idea is pretty much directly will give you the general lower bound as well. So now, we can ask, is this lower bound actually tight? Can we, break it in square root n samples plus queries? And so the natural thing to do that would be to, get square root n edges. And then, you'd end up with two edges from some cycle. But the problem is that we don't actually know which edges this is, right? We've collected all these red edges here, but we don't know which two are in the same cycle. We would like to sort of query this 4 cycle here, but, offhand, the naive way of doing that would maybe be to query all pairs of edges, which, is clearly very wasteful and not the right thing to do. So to get around this, the natural thing to do is to build a sketch of the ordering. So we'll sample square root n vertices and we'll sort them. And now we note that if we truly had a total ordering, then if given any element I, we could sort of place them into their bucket here. So you could tell me that, oh, I is bigger than x1 and less than x2, and we can do this highly efficiently via binary search, right? So you have this sketch. And now we note that, with this sketch, we can actually find which two edges belong to the same cycle. So, they should just be the edges that end up in the same bucket. And now we can sort of like just query all the endpoints that end up in the same bucket. And this is actually how we get the upper bound here of square root n as well. Good. So now how do we generalize this to decision lists? So essentially, there's sort of an ordering in decision lists as well. So, you have the ordering of the literals. So you can think of like ordering the coordinates by how important they were in the decision list. Like the first thing is the most important, the last thing is the least important. But there's some difficulties here. So for instance, if I have an x1 and x2 with the same function value, it's not exactly clear how to compare them because, like normally you want to say that, oh, this one is a 1 and it's in front. So I can kind of use my queries to see that, oh, there's something I could flip in here that would change the value of this point, and that should make me think that it's bigger, right? But sort of the difficulty is that if they have the same function value, then I really don't know which one is bigger, and so this leads to some complications. We can still sort of find an ordering, but it ends up being a little bit more murky. So essentially what we end up with is sort of these like interspersed ordered lists where, we'll get x1 and x2 and, maybe all the x's evaluate to 0 under f, all the y's evaluate to 1. So we get x1 and x2, and we know these are all smaller than the y's that we've sampled. But we don't know how they stack up to each other. Maybe there's something in between them, so one is bigger than the other, but we just don't know this. Similarly, we have y1, y2, y3. They're all bigger than these x's and less than these x's, so they could lie kind of in this interval as the picture to maybe have. But we don't exactly know where they lie and how they, lie with respect to one another. But really, so it's kind of, it's close enough to an ordering in some ways. So, maybe it's workable. But the issue is, it's not exactly clear what a violation is for a decision list. For total orderings, like it's very clear that, cycles are kind of can never happen in total orderings. And like, this is kind of the only bad thing that can happen. But it's much less clear what this is for decision lists. So when should we be rejecting? And, maybe a candidate answer is to say, we look at firing rules. So maybe we look at the firing rule of y5, and we say if that literal was satisfied in x1, then something has clearly gone wrong. Because, we should have been reading this literal first because it had higher priority. So if it fired, then, f of x1 should be 1, but it was 0. So we should reject in this case. So that's a candidate answer. But, we don't actually know what the firing rule of y5 is. And so, how do we actually implement this? We somehow would need to figure it out. And it turns out that actually the key idea is that we can brute force to find the firing rule of y5, essentially, roughly in the amount of time, in time proportional to the number of rules between x3 and x4, right? And so if there's not a lot of rules between x3 and x4, we're actually relatively happy. But if there are many rules, we could be in trouble. And in fact, in general, like there could be many rules between sort of two elements of the bucket. For instance, actually, if you look at a conjunction itself, these will have, every block will have, there'll only be like, two blocks or something, and they'll have omega of n length. And so, we can't, even if we truly had a decision list, we can't even rule out the existence of big blocks. But it turns out that we can use a separate argument to handle the case of big blocks. And the key insight there is that, if you're telling me that there's many rules that lie in between x3 and x4, then, there can't be many blocks that have this, right? Just by a counting argument. And that's kind of, maybe the high level idea of how we're testing these decision lists. Anyways, that's all I have. Thanks for listening.